Good afternoon. I'm James O'Brien. I'm representing the Timber Titan Senior Design Team. I'm going to talk to you a little bit about our Rainbow Bridge design for use here at Temple's campus. This is our abstract. Basically discusses the issue at hand and how we're going to plan to address it, which I'll get to over the next few slides. This is our team. It consists of 3 civil engineering students, myself, Mitchell Wilson, and Nick Calabrese, and 1 mechanical, Jeff Price. Our advisors, Dr. Miller, and our course coordinator, Dr. Ryan. So the issue at hand, basically we're trying to alleviate congestion, commuter congestion, both vehicular and for pedestrians at the intersection of 12th Street and Paulette Walk. Over the past couple years, there's been a lot of growth at Temple, a steady increase in enrollment, construction of new buildings, new dormitories, all sorts of things. So it's only going to add to the hecticness of this area. Our solution for this is to build a pedestrian bridge over 12th Street along Paulette Walk, hopefully just to increase the efficiency of this intersection as a whole for everyone using it. This is the basic structure of our substructure. It consists of 4-piece members and 3-piece members interwoven over 5 different cross pins. Why the Rainbow Bridge? The Rainbow Bridge is based off a quarter circle as opposed to a lot of other arch bridges which are based off a half circle. It allows you to meet the height requirement you want without having such a drastic slope, which will help us comply with the Americans with Disability Act regulations. And it allows us to use less materials. Other benefits, like in terms of the view of the university, it coincides with the 2020 plan, which actually asked for, or they are looking to increase the overall efficiency of commuters all around the area and all around the campus for safety and just general efficiency to get around. Here's our project overview. We started with the design and then had to base it off of the location, so the allotted space available, which then got us into our substructure, and then had a lot of different regulations to withstand from both PennDOT and the ADA, which would lead us to our final prototype. These are our technical constraints. 2 I want to focus on are the clearance height of the bridge and the ADA requirement. PennDOT requires that you have at least 18 feet above roadways, and the ADA requires that you have a maximum of 6% slope for any handicap accessible ramps. This is the member length determination for both the 3-piece and 4-piece members that make up this substructure. This box down here is basically the height of the clearance we want above the street, above the curb line, and then the width of the street. And through geometrical analysis, we were able to obtain the different lengths for both the 3 and 4-piece members. Here are the final lengths, the longer members being 38 feet and the shorter members being just under 20. These are some pedestrian counts we had to help us determine the live load to distribute over the bridge. These 2 rows at the bottom in red are the highest counts we had, the busiest time of the day. The highest count we had at any 20-minute interval was just under 700 people, and we're going to use that number moving forward to calculate our live load. Here for the live loading, we took the average weight of a male in Philadelphia at 191 pounds, and then multiplied that by that largest amount, that traffic count that we had, and divided it by the surface area of the bridge to get the live load, which came out to be 54 pounds per square foot. That's well under the PennDOT minimum of 80 pounds per square foot, so moving forward in any testing or design, we're going to use 80 pounds per square foot, which will ensure that it's sturdy enough to withstand this live load. Here's the dead load. Basically goes off the members and their size, so the cross-sectional area of all the members is a foot by a foot, multiplied it by their length, and use the density to determine the weight. Again, the cross pins have a 16-inch diameter, and use their length and density to determine the weight, with a total overall dead load of just under 46 kips. For the snow loading, according to ASCE Table 7.2, this bridge falls under Category B, That's for any bridge with the maximum height under 30 feet. That'll give us our exposure factor, and through the analysis here, our total snow load is just above 42 kips. Wind loading. Wind loading is usually governed by location and bridge geometry. The most prone area to any wind loading is the area perpendicular to the direction of travel. So in our case, if the bridge is extended this way, the wind coming across will be where it influences the most. Fortunately for this design, the greatest height difference for any area of contact is only 12 inches, which will cause such a minuscule difference in pressure difference. So the wind loading is pretty much negligible. These are the member forces. Here are the 5 different pins that would be across. This is adding up all the forces, the live load, dead load, and snow load, and then distributing it over the 46 total nodes that we have across the entire bridge. We're using this force per node of a little over 6,000 kips to determine the strength that we need for the member connections at all of these nodes. And I'll get into that right now. Here's just how we use method of joints to determine the compressive forces in all the different members, just so when we connect them we can design the connections and bolts all to be able to withstand these loads. These red numbers here are the force per node, and the black numbers and lines is the compressive forces within the members at that joint. Thermal expansion. Since this bridge is located in Philadelphia, we all know there's going to be subject to drastic temperature changes, and these sudden temperature changes may cause the wood to swell or contract. So we analyzed this and figured out the maximum amount of change that would occur in the length of the beams. For the long beams, it's just under an inch, and for the shorter beams, it's just under half an inch. This number here, 69 minus 1, that's the largest temperature difference that there's been in 1 month in the past 20 years or so, with 69 being the high and 1 being the low. These are our member connections. This is the bolt determination, determining the right bolt size we want to use for the connections. We use the maximum force the bolt would be able to withstand, and the maximum force that 15,210 psi. That's the maximum force applied to any one node, which would give us a necessary diameter of just under half an inch. Again, we did a similar process but testing the wood for its failure. This is the maximum amount of stress the wood would be able to undergo before failure, and using that with the maximum force at any one node, again it's under half an inch for the diameter necessary to be able to hold that. Those 2 previous slides were both designed for only one connection with one pin. We decided to go with 2 bolts, both half an inch, to give us safety factors of 2.48 for the bolt and 2.95 for the timber. We used a similar process again to determine the thickness of these collars that we wanted in these connections. The maximum stress that it will be able to withstand is 39,000 psi. And then using that, and again the maximum force that would be at any one given node, gave us a thickness of a little under half an inch. We decided to go moving forward using 1 inch thickness, which would give us a safety factor of 2.39. Here's just a picture of what the connections would look like at each different node. There's slots here for 2 pins for each member, and then space allowing it to expand or contract based on any temperature differences. This is some testing we ran in Stab Pro. We compared pin connections and fixed connections. The fixed connections help a lot more in terms of keeping the structure very rigid and tight-knit. The entire thing is based off compression, so everything needs to be locked in really tight and holding its position. So that's the best way for us to design this. And it gave us a maximum deflection in the Y direction of well under an inch. Level of service is based on a scale ranking from A to F. Typically in urban areas, it drops down from C to E. It's based on the amount of square footage an individual person would have while using the structure. This is how we calculated it for our bridge. We took this grid here, which is 22 feet, which would be the width of the bridge, by 26 feet, which is the width of the street. The maximum amount of people we saw in this grid, and then implemented it over the full surface area of the superstructure, and it helped us calculate a level of service in the D range, which is 7.6 feet square per person, which is typically pretty good for a pedestrian bridge in an urban environment. Material selection, I might have mentioned before, we're using timber. It's a renewable resource, aesthetically pleasing, and definitely cost effective. The type of timber we're going to use is Douglas fir because of its structural benefits. It's very high in rigidity, able to retain its shape, and low with cracking. These are non-technical constraints. One I want to focus on is the sustainability to help minimize any decay and protect the substructure from the elements. What we're going to use to cover it is copper naphthenate. It's non-toxic to plants, very easy to get a hold of, easy to apply. This is our cost analysis. If Temple chose to build a full-scale model, it would be a little bit over $100,000, which is pretty cheap in terms of building a structure this big. This is how we approached our superstructure design. The biggest difficulty with designing the superstructure is ensuring that the loading would be treated the same way once it's passed from the superstructure into the substructure. So we had to make sure all the loading would be distributed onto the 5 nodes, keeping the integrity of the substructure to be able to support this. So we started by building the decking at the top, above the 3 nodes, and then base these stairs. The bottom half of these stairs will rest on the members of the substructure, which is fine because that load will be transferred into that pin. And then the rest of the stairs get connected above the other pin, which will ensure that the loading will be transferred accordingly. Here's the final overall layout. This is the final layout at the site. These are all planter boxes to ensure that people don't try and cross the bridge underneath the bridge and to keep people from under the ramps or under the stairs. Here's a view from a little bit further away. This is Anderson and Gladfelder. That's the library up top. You can see the bell tower. We thought the best way to allow for the most efficient intersection here would be to excavate this area in front of the library where there's trees and that little grass hill. It would allow for a better flow from the bell tower down 12th Street to get basically out of the way for people who are using the bridge and just open up the area as a whole a little bit better. Adding that superstructure added an additional weight, an additional dead load. This is a stab probe analysis with that additional dead load. After running it, again we had a deflection of well under an inch. And then here's running through the design that we used for our substructure for the member connections. Again, the 1/2 inch 2 bolts would suffice to withstand the additional dead load added by the superstructure. And our safety factors would drop a little bit. For the timber would be 2.33 and the bolts would be 1.96.
Questions?
The copper naphthenate, would that need to be like reapplied?
The copper naphthenate that we would use for the substructure, I'm pretty sure it's just a one-time application in terms of applying any sort of like lacquer or material to help the decking and the ramps. That would be a little different. That might need to be applied more frequently in terms of the service, but the copper naphthenate for the substructure is just a one-time use.
The questions? So the ramps that you have designed, how long are they? These are wheelchair accessible ramps?
They are in compliance with the ADA maximum of 6% slope. On the library side, they extend about a little over 50 feet, and on
Well, I mean, the total ramp length.
the
Like,
total,
how many feet is it if you start at the bottom of that ramp and walk back and forth through those S-curves to the top?
It's 386 feet
386.
total length.
pretty extensive.
Have you ever tried to push a wheelchair 386 feet up the ramp?
I have not.
Okay. One other question, and it's not clear from your drawing, so hopefully you can clarify this. If somebody is walking from the train station and they want to go to the library,
Yes.
do they have to go over that bridge?
Pretty much,
Okay.
unless they want to walk further down 12th Street to cross. These planter boxes here come out about 50 feet past, so if you're walking underneath the bridge, once you're out in the open, it'll be about 50 feet until you can access the street, just to keep people kind of away from the general location, since cars won't have to stop anymore, just to kind of keep it safe, as safe as possible.
And how much space is there between, whether it's the ramp or the stairs, and the edge of the sidewalk? So if somebody's coming from, say, the train station and they want to make a left and walk, or they want to make a right and come up to the engineering building,
There's 8 feet.
8 feet of walking space.
Mhm.
Okay. Any idea what the traffic for that type of traffic pattern might be?
I'm not sure.
Other questions?
Yeah, sort of a question, comment. On the ramp system, when you turn the ramp from one direction to the other, there's a flat place there,
Yes.
correct? Okay, so there's a,
Mhm.
you know, in stair systems and ramp systems, you do have flat,
Uh-huh.
sort of resting places in a sense, so
Yes.
that's good.
That's also why we tried to do the decking at the top flat, because one of the other difficulties with the space allotted is we have to put the ramps on opposite sides, so we didn't want to make it any more difficult to have to get across the bridge.
And you could also pull out the stair system to a greater distance to flatten out the stair system a little bit.
Other questions?